This meeting is being recorded.
We saw on the last slide shown from section 5.3 this concept of optical activity being introduced here. So what exactly is optical activity? So we're told here that enantiomers will have opposite configurations. So we saw that previously, that if the first enantiomer is an R, the other would be an S, each of which would rotate, each of these enantiomers will rotate plane polarized light in opposite directions. So this rotation of plane polarized light that's possible, that is what this term optical activity refers to. If something's optically active, it will rotate plane polarized light. So let's take a step back and review what's shown here is the electromagnetic waves. So we have these electric field and magnetic field, which are perpendicular to one another. And we can see shown in red here, the electric wave, which is oscillating in a certain plane, and then we see that magnetic field is in a perpendicular plane. So this electric field that's shown, this is called the polarization of light, of a light wave, we should say, of light wave. So what we can do is we can use a polarimeter, and we'll look at the full structure of that, to send polarized light through a sample and see exactly how much rotation the compound does to that polarized light. So we have a standard value, it's rotated when sent through a compound, and then we can measure the difference to identify the angle of rotation and what compound we have present. So we have light waves, and they need to travel in only one plane. So what we see here is that unpolarized light here indicates that we have random waves coming out from that central point, that point of the light origin, and they're not polarized, they're not in only one direction. So what we do is we will pass these light waves through a filter, so that's shown here and here, and only one plane, right, will pass through this filter, and if our receptor here, our receiver here, our filter on the other end is oriented in the same direction, light would pass through. If we have it closed or oriented in a different direction, no light would pass through. So we pass this plane polarized light through our sample using a polarimeter, which is shown here. And the polarizer is that filter that allows only that single plane of polarized light to pass through, and that's what we see here. And once it enters this area here in our sample tube, in the polarimeter tube, you can see that that light is rotated at different angles. And the degree of rotation can be analyzed using this other filter here. So we set this zero marker, and then based on which angle of rotation, either to the right, we will call a positive rotation, or to the left, we could call a negative rotation. That helps us identify one enantiomer from the other. So we know that enantiomers will rotate in opposite directions. They will also rotate equal degrees, rotate the plane of light equal degrees. So if the R compound rotates 20 degrees to the right, the S compound would, or the S enantiomer would rotate at the same amount, 20 degrees in the left direction or to the negative direction. So this can be dependent on both concentration and the path length of the light that's traveled. So we have to standardize our formula here and to measure the optical rotation of our sample. So we call this overall equation the specific rotation, and that's what that alpha value there is telling us. And we have to record the specific temperature and also what wavelength of light is passing through our sample. This is commonly what's called the D line of sodium, and it's approximately 289 nanometers. That is the wavelength associated with these types of polarimetry experiments. So we standardize this again, not only by the length of the path length that the light travels, but also the concentration of our solution. And that will be given generally in grams per milliliter units. And up top here, this is our observed angle of rotation. So that observed angle of rotation, as we mentioned, has to do with the concentration and the path length. So these would standardize our specific rotation value for our compound by dividing by both the concentration and the path length. So here's an example of what we could see. We have the two enantiomers of 2-bromobutane shown here. One is R orientation on the left here, and the other is S orientation. And we could do our prioritization to confirm this, right? We have 1, 2, 3. So we would see that this is definitely our R compound, our R enantiomer. And then we have 1, 2, 3. And we would think it's R, but then we know we need to invert it because our lowest priority is on a dash and not on a wedge. So this would definitely be our S enantiomer over here. So notice they are these angles of rotation, these alpha values, they're recorded at the same temperature, 20 degrees Celsius, and this D represents the wavelength, the D line of sodium, and we recorded this would have a negative angle of rotation, so that would be to the left rotation, we could say, right? And then this would be our right rotation, and this would be a positive value, but the same magnitude. So there's no direct correlation between an R enantiomer rotating to the left or the right, or an S enantiomer rotating to the left or the right. That can only be determined experimentally. So you know that you have an R enantiomer, but you put it into your polarimeter and you find out that it rotates plane polarized light to a negative angle. Whenever we have a left rotation or a negative rotation, we call this levorotary. And if we had a positive rotation, we would call this dextrorotary. So you'll see commonly these terms dextrorotary or plus sign used interchangeably, as you would see a negative or levorotary. So we have down here, we have this compound. We're told it's the S configuration. We know it's optically active, and its optical rotation is negative. And we're told at 20 degrees C, it's negative at 20 degrees C, but it becomes dextrorotary at higher temperatures, around 100 degrees Celsius. So again, there's no direct correlation between the R or S compounds. We have to record the angle of rotation experimentally to determine which way our enantiomer rotates plane polarized light. So the last thing that we'll look at here in these last few slides has to do with something called a racemic mixture, where we have an equal amount, a 50-50% mixture of each enantiomer. So the R and the S mixture is 50-50. If we had one enantiomer in excess to the other, we would still have an observed optical rotation, but it will be less than if we had 100% or a pure enantiomer. So we can actually calculate our expected angle of rotation, or our percent, what's called an enantiomeric excess. That's what the percent EE is for, enantiomeric excess. If we're given all the other values, for example, down here, this equation can be used if we're given the observed angle up here, and then we're given the alpha value for a pure enantiomer down here. we can plug in these values. So we would have a negative 4.6 divided by negative 23.1. So we know that that would be our pure R enantiomer, right? This guy here. And we've observed this angle through our polarimeter. We've observed this specific rotation, negative 4.6 degrees. And we multiply that by 100, and this would give us a value of 20% enantiomeric excess. So we know that we have 20% more of the R isomer than the S isomer. So we'll take a look at some more definitions and some more terminologies from this chapter in section 5.5.